Hello, everyone. Welcome to our live session for Monday, July 26th. We are excited to have you all here. My name is Matthew, and I am one of the course staff for our online classes, but we know that people join us from a variety of places. So however you found out about us, we are happy to have you here. We're going to answer a bunch of your astronomy and astrobiology related questions. I will hand this, a thank you to Vicky, who's running our stream today. I'm going to hand this over to you, Chris. So Professor Impey, who will welcome everyone, and we will get started with your questions. Please post those in the chat, and we will grab them from there.
Okay, thanks, and welcome everyone to another live Q&A session for our online courses, and anyone else who happens to stop by. Ready to take your questions on astronomy.
Excellent. The first question is from an email. Gonzalo asks, considering ordinary electromagnetic broadcasting signals, for example, TV, radio, and similar activities, and ignoring special transmissions like the Arecibo message, what's the maximum distance at which these signals could be identified as artificial signals before being indistinguishable from background noise, regardless of the technology used on the receiving side?
I know the answer to this very well because about a decade ago I was asked to be on NPR to talk about it on their science show, and they had a nice hook for the show, which was the idea that we've been broadcasting, commercial TV to large audiences since the 1950s or so, and so the premise of the show was that I Love Lucy, a sort of American sitcom of the 50s and 60s, the bubble of TV signal from I Love Lucy has now, of course, reached 50 or 60 light years from the Earth, which encompasses thousands of stars, and those civilizations on planets around any of those stars would be receiving our early TV broadcasts and either thinking, wow, that's impressive TV, or these people are clearly not worth our consideration. It turns out, unfortunately, to be a faulty premise. Even with megawatt transmitters, which we've had since the 60s, they're now hundreds of megawatts for a TV transmitter, and the leakage of that radiation, because it's not beamed, it does broadcast out and it does escape the Earth. If you do the math of the strength of the signal, the inverse square law kills the strength of the radio signal so quickly that it drops below the level of the microwave background radiation before reaching the orbit of Neptune. So unfortunately for this premise, and I've actually seen it falsely played out in the popular literature a number of times since I did that show and it got put on their website, there's no way our inadvertent broadcasts from going back half a century would be detectable outside the solar system. Sorry.
That's actually really interesting. I was not familiar with that. That's fantastic. Thank you, Chris. The next question is from Sanchita Ghosh, who asks, is it possible that we are all Martians who escaped to Earth when Mars turned to a hostile environment? Have we emerged here on Earth after genetic engineering?
Well, there's sort of two answers to that question, because there's two ways to take that question. The part of the question that alludes to the fact that Mars had ancient forms of life that evolved to be superior forms of life, and then they left the planet as it dried out and became uninhabitable, and that's who terrestrial people are, is unfortunately that doesn't fly, because there's no evidence, archaeological or chemical or imaging or anything else, that shows that Mars ever had an ancient civilization. Obviously Percival Lowell thought there was a civilization on Mars. He misinterpreted the canals to be artificial constructs. So there's no sign of an artificial civilization on Mars. And on the flip side, there's no evidence that humans were ever genetically originating from anywhere else. We are part of this tree of life, which is the same genetic material that applies to everything on Earth. All microbes, plants, animals, etc., are one genetic material. So there's no indication that we evolved from creatures of a different planet. We are terrestrial. However, the interesting part of the "we are all Martians" hypothesis is the hypothesis that life on Earth began with a Martian origin microbially, and that's because Mars was almost certainly habitable 3 to 4 billion years ago. Life on Earth started at a time we don't fully understand, but at least 3.7 billion years ago, maybe as much as 3.9 or 4 billion years ago. But we haven't seen direct evidence of that. That evidence is lost in the tectonic activity and climate weathering of the Earth. There's just no physical evidence. So it is conceivable that life started on Mars 4 billion years ago, and then because it's not difficult for Martian meteorites to get ejected from the weaker gravity of that planet compared to Earth, and then fall towards the sun, where the gravity is stronger. So Martian meteorites come to the Earth far more frequently than Earth meteorites go to Mars. It is possible that life started on Mars 4 billion years ago or thereabouts, was blasted off the surface, contained and protected in a meteorite, which landed on the Earth and seeded life on Earth. That is technically possible. And it's hard to assign a probability to it, but that's a hypothesis that is still in play.
The next question is from David Learning, who's on with us live. How is the mass of a host star of an exoplanet approximated?
That's a good question, because we don't usually measure the mass of any star directly. Mass is the fundamental property of a star. If you tell an astronomer the mass of a star, then the astronomer, and assuming it's a main sequence star, the astronomer can tell you how long that star is going to live, how much energy it'll put out, and how it'll die. So it's fundamental property of a star. But when we measure exoplanets, we of course see the star. The star is millions or billions of times brighter than the exoplanet that orbits it. So we have a stellar spectrum, and really typically that's all astronomers have when they try to understand stars. They have a spectrum of the star, and if they have a distance and an apparent brightness, they have the luminosity. Armed with the luminosity and a spectrum, you can get the spectral class of the star, and you can decide whether the star, for example, is a giant star or supergiant or a dwarf star or a main sequence star. And that in turn, with the luminosity, tells you the evolutionary stage and therefore the mass of the star. So we can infer the mass indirectly from having a spectrum, and that works the same for an isolated star or a star that has exoplanets around it.
The next question is from an email. Torsha asks, in the online class you mentioned robotic telescopes. How are they different from the other space and ground telescopes, and what are they used for?
Well, robotic telescopes, essentially all space telescopes are de facto robotic telescopes because there are no people there operating them. They have to work completely autonomously and remotely by computer commands sent from the Earth. So all space telescopes are robotic telescopes. That's how they're designed. Now, some subset of terrestrial telescopes are also robotic telescopes, which means they don't need a human attendant. They don't need telescope operators. They may need engineers and technicians to check them out occasionally, if not every day. But there are a number of robotic telescopes on the Earth, and they range from small telescopes. Amateur astronomers have fully robotic, automatically controlled telescopes. In fact, some of the small telescopes you can buy as an amateur astronomer called Go-To telescopes are essentially modest robotic telescopes, to telescope arrays that are looking for exoplanets, up to mid-sized telescopes of 1 or 2 meters. So there are dozens of Earth-based telescopes doing research that are essentially operated remotely. It saves a lot of money because telescopes need to be in remote locations on high mountaintops, and that's expensive to live there or maintain it. It's difficult to reach. It takes a long time to travel. And so if you have a robotic telescope, you can make it a fairly cheap operation to run.
The next question is from Wiedmond, who asks, what about a Venusian origin for life on Earth as opposed to a Martian origin?
That's an interesting hypothesis, too, because Venus also was more habitable than it is now, same as Mars. It's not very clear, however, that Venus was completely habitable. I mean, the idea is that before the episodes of intense volcanism and the intense runaway greenhouse effect that made Venus's atmosphere much thicker than the Earth's and incredibly hot, Venus, as a very similar to Earth-sized planet, it's within 10% of the Earth in its properties, could indeed have been habitable. Remember, it's a fair amount closer to the sun, so it's on the inner edge of the habitability zone. The early sun was a little dimmer too, so that actually helps the habitability of Venus. So it's plausible that Venus was habitable 3, maybe 4 billion years ago. A Venus rock traveling to the Earth is fighting against that strong gravity, similar to Earth gravity. it's also fighting against the sun's gravity to travel outward in the solar system. So Venus meteorites, if you like, do not reach the Earth with any great frequency at all. We've identified probably over 100 now, maybe 120 Martian meteorites. I mean, that's a small fraction of the total that exist, but we found 120 Martian meteorites. I don't think we found a single example of a meteorite that's been claimed to be a Venusian meteorite. So that, in a sense, answers the question.
The next question is from, let's see, here is from Wendy Traver from email. Can you please discuss the significance of methanogenesis on Enceladus as discovered by Cassini? So the presence or generation of methane.
Right. Cassini was a spectacularly successful planetary mission, and it's completed its mission now. Of course, it's destroyed itself in a very spectacular ending, almost Wagnerian. But for a decade, it was doing incredible work in the Saturn system, looking at the rings of Saturn, of course, and studying many of the moons. And it was Cassini that first swooped through the icy geyser jets of Enceladus and not only told us that those jets were salty and had possibly the ingredients for life, but that this tiny moon could be habitable. And we've since found evidence of methane, chemical methane, in the jet emissions. And that's a sort of a biomarker, because methane on Earth is associated with life. Not exclusively, however. Methane can come about from natural means. And so there's a debate, basically. Methane alone does not prove a biological origin. Witness the debate about Martian methane. Martian methane's at a level of few parts per billion, which is 1,000 times less than methane on the Earth, where there's no question life is involved. So when you have a very small amount of methane, you don't get to say that it's biology. And unfortunately, Enceladus is in that situation too. It's very subtle and slight amount of methane. We've not necessarily seen other molecules that would directly implicate life, and so the jury is out. We're going to actually need another space probe to really answer this question.
The next question is from one of our live participants. Smayana Twitch asks, how does or could quantum computing help with research in the fields of astronomy and astrophysics?
Well, quantum computing will help essentially all research fields enormously, because it increases the power of our supercomputers by really orders of magnitude once it's fully to scale. The gist of quantum computing is that instead of the sort of enormous numbers of binary on and off states in a semiconductor that form the basis of modern electronics, you create what are called qubits, which are entangled states, which encode the possibility of a 1 or a 0, but also a mixed state. And it turns out that doing that allows you to parallelize a lot of computational tasks and make them much more efficient. So quantum computers are intrinsically more efficient than normal computers. At the moment, I don't think more than a few hundred qubits have ever been demonstrated in the lab, and that's obviously not enough to make a supercomputer or even a regular laptop computer. So this field is probably 10 to 15 years away from maturity, but when it gets mature, it will fuel enormous amount of astronomy research. We have supercomputer simulations of everything from black hole jets to the formation of the universe to how planets form, and all of them drive computers pretty much to their limit to get good data, to get good simulations. So quantum computers will accelerate that work enormously. But the same is true of almost any field of science. So everyone's waiting for quantum computers.
Thank you. Federico Giuliani, who's on with us live, asks, how can we demonstrate that time is a real physical phenomena instead of a human perspective?
Well, we can demonstrate it because we keep time in different ways. So there's obviously human felt time, human experience time, the arrow of time. There's sort of physiological time. Humans have body clocks, and all animals, basically everything in the animal kingdom, keeps time in various ways. These are associated with diurnal cycles or lunar cycles. So, but there is time beyond that. And I think the heart of time would come down to the atom. So atoms are basically encode or embody a set of vibrations and oscillations, the natural frequencies of atoms and their quantum states. And that is a fixed number in oscillations or cycles per second. And so that essentially is an intrinsic timekeeping piece. Another version of timekeeping, of course, is involved in radioactive decay. That's a nuclear process where massive atomic nuclei are unstable and they decay with the emission of radiation and other particles on a very specific timescale called the half-life. And essentially different heavy elements have different half-lives. And so those are clocks built into the nuclei of atoms. So we absolutely have timekeeping that is independent of our perception of it in physics.
The next question is from one of our emails. Jan asks, did the first stars in the universe cluster into galaxies? And did those first stars have enough heavy elements to have or form planetary systems?
That's a good question. There's a hypothesis in cosmology, it's been around for a while, of what are called population 3 or first generation stars. And it's the speculation of when the first generation of stars were, and in particular, relating to the question, whether galaxies formed before stars. The best guess, it's hard to tell. We have to use simulations to get a sense of how this might have worked. But the best speculation is that the initial gravitational contractions would have formed things at the size of stars, or very large stars. Actually, the first generation of stars could have included stars of several hundred times the mass of the sun. But those simulations do suggest that massive stars formed first and then were aggregated on larger scales into galaxies. And so that process, it was a sort of a bottom-up process. And the time of that is hard to tell. It could have been within 100 billion years, 100 million years of the Big Bang. Now, those first generation of stars would, of course, have consisted almost entirely of hydrogen and helium. So they were not formed from a gas or plasma that had any heavy elements in them. And so that actually affects the properties of a star. The way that stars form depends on the amount of heavy elements in them. So the sun, of course, already formed billions of years after the universe evolved and had heavy elements built into it. Those heavy elements in physics terms sometimes help in a collapsing gas cloud to collapse. They allow so-called cooling through the molecules or the atoms and their transitions. So heavy elements in a gas cloud actually affect the way it forms stars. And so people had to do simulations with computers about how this first generation of heavy element poor or absent stars actually formed. And that's part of what suggests that they may have been very massive. No one's observed any of these stars yet, and that's one of the goals of the James Webb Space Telescope and our big new ground-based telescopes, to actually observe directly this first generation of stars in the universe. Lost your Matthew, your audio.
Sorry, I missed the unmute button when I tried to click. The next question is from one of our live participants, Mythical Savagey, who asks, what is the difference between a singularity and a so-called ringularity, or a ring singularity?
So in principle, when a black hole forms and is surrounded by an event horizon, which is the barrier to information and stops us essentially from seeing a singularity, what lies inside the event horizon does depend on the rotational state of a black hole. So if you have a rotating black hole, especially a rapidly rotating black hole, in the theory of general relativity, the singularity, which would just be a point, a cusp of mass density, actually turns into a ring, and that's a ring singularity. That's a very hypothetical construct. It's just calculated from the theory of relativity. Singularities, of course, are unphysical. They're cusps, they're infinities, if you like. And the ring singularity doesn't change that. So if you can imagine it, the ring singularity is a one-dimensional ring where at every point along the ring is infinite mass density. And it sounds nonsensical, and it is physically not a very sensible concept. So people have no idea whether ring singularities or singularities at all exist. There's a cosmic censorship hypothesis that came from Stephen Hawking and in the 1970s, and it says that there's no such thing as a naked singularity. And Roger Penrose was also behind this theorem. So it may be that we can never observe the singularity or know if nature has ever made a ring singularity.
Excellent. Thank you very much. I'm going to mention, so Nextver has asked a question about recommending a pair of binoculars or telescopes. We have an amateur astronomy stream on Fridays, and that would be a really great place to come and ask that. So I just wanted you to know that we're not skipping, or, we're not ignoring your question. We're just going to skip over it because we have a better venue for that. So Sniff 250 asks, could there be living microorganisms on Mars? And if so, could we have accidentally killed them off by sending rovers with Earth contaminants on them to Mars?
The answers to those questions are yes and no. There could be existing microbes on Mars alive right now, not fossilized or dead life, but they would have to be underground. The surface of Mars is sterilized, essentially. Mars has a very thin atmosphere, no magnetic field to protect it from solar radiation and cosmic rays, and micrometeorites, of course. So the surface of Mars, the regolith or the soil, is bombarded with micrometeorites and high energy radiation. And so it's thought that it's sterilized down to about 4 centimeters or 1.5 inches. And that really means there could be no microbes, as far as we understand them, on the surface of Mars or near the surface. However, underground is a different story. We have strong indications of subsurface ice, strong indications of subsurface water. The water would be kept liquid by pressure from the surface rock and by mild heating from the rock in the interior, because Mars is not geologically active. So it's entirely plausible there are aquifers, there's subsurface water, and therefore there would be all the conditions suitable for life. There's local energy source, not sunlight, of course, but geological heating or radioactive decay, for example. There would be liquid water, and there's carbon-rich material. So yes, there could be subsurface microbes. And of course, because the surface is sterilized, when we put things on the surface like rovers or landers, we don't really contaminate it. First of all, those landers sterilize themselves when they come through the Martian atmosphere, and the same objects, once they're roaming around or sitting on the Martian surface, are being sterilized just by the radiation that they're subject to. So because the Mars surface is sterilized anyway, and the objects we put there get sterilized, we haven't contaminated anything, and nor have we killed Martian life, might it exist, because if it exists, it's underground.
Thank you. The next question is from Terry Trevino, who sent an email asking, can we shape electromagnetic fields to protect ourselves on Mars? Let's see. Okay, so can we shape electromagnetic fields to protect ourselves on Mars or Earth? And there's a follow-up that I'll ask afterwards.
In principle, yes, we have technology that would allow us to create electric and magnetic fields to act as protection. In fact, NASA, this sounds a little out there for NASA, but NASA's chief scientist, in fact, was involved in a study of actually putting an artificial magnetic field out well beyond Mars in the direction of the sun to create a magnetic barrier to the solar wind, which is really interesting because Mars, if it ever had a magnetic field, and it probably did, it lost its magnetic field early. And it's the magnetic field of the Earth, for example, that shelters us from solar radiation and the solar wind. Mars has no such protection, but there's actually a proposal from NASA of how you'd put an artificial magnetic field not on the Martian surface, but out there in front of Mars to deflect the solar radiation and protect Mars that way.
Excellent. And then the follow-up question is sort of related. Is it possible to choose a landing zone on Mars where an electromagnetic field sort of already exists that would protect us?
So there's no preferred place to go to Mars for human habitation where you have any extra degree of shelter. So no, Mars has no substantial magnetic field anywhere around it. So there's no place you could pick that has some magnetic field or a modest magnetic field. If you wanted to set up an electromagnetic field and protect a base, you could do that. Another idea, which actually may end up being easier, is to use lava tubes. So on both the moon and Mars, there are lava tubes. The moon has had some mild volcanism in the past. Mars was heavily volcanic in the past. And so people have already identified from imaging orbiters lava tubes. And in some cases, these lava tubes are underground with a sort of thin cap, if you like, of regolith or lava that shelters them. And some of these are hundreds of meters across. So we've identified, especially on the moon, but also on Mars, lava tubes that are tens or hundreds of meters across and tens of meters underground that are protected by a thin cap of rock. And that's almost a perfect place to build a base because you have the shelter you need from the cosmic radiation.
The next question is from Wiedmund, who is on with us live, who asks, do you know of any accurate virtual reality observatories that would allow a tour of our galaxy?
Virtual reality tours of our galaxies, that's interesting. The observatory or facility that has the capability for this is the Hayden Planetarium. The Hayden Planetarium, is a research operation as well as a facility for the general public. And they, in their planetarium shows, they've used virtual reality goggles and so on, but they, of course, have an immersive dome display which allows 3D exploration of the universe, the entire universe, as well as the galaxy. The data that underlies many of their shows, which is used by researchers as well, is a highly rendered version of the Milky Way galaxy that includes tens of millions of stars, the gas clouds, nebulae, and so on. And it can be explored in 3 dimensions. And they work that into their planetarium shows. But for people using that database as a research capability, you can do it with virtual reality. Now, I don't know that these abilities to do VR exploration of their 3D data are available to the general public. They tend to be only for the researchers and the staff. But that is the first place you would look. And actually, the data that they use is available to the public. It probably takes a pretty phenomenal amount of computing power and storage to use it, but it's not proprietary.
I also wanted to mention Worldwide Telescope, which is an online resource that has sort of fly-throughs of the galaxy and objects in the galaxy. So I don't know if you can make it look virtual, connect it to virtual reality goggles or anything, but right. That might be another free online resource to try out. Emma Kanakande asks, what would strange matter look like in a neutron star, and could it exist?
Well, so people are not entirely sure of the physical state of matter in a neutron star. It's essentially nuclear material. So a neutron star in simplistic terms is an atomic nucleus with an atomic number of 10 to the power 57. It's the atomic nucleus that's the size of a pretty massive star. Now, operating under that intense gravity, just short of what you would have in a black hole, nobody really knows what the state of matter is. There's quarks, which are the ingredients of neutrons, are contained. There's a containment mechanism for quarks such that they're almost never seen in the lab. They can only be liberated for tiny periods of time in an accelerator. There's speculation that in the neutron-rich material under incredible pressure, the quarks may be liberated more often. It's what the quarks do that leads to the idea of strange matter in a neutron star. At the moment, we really don't understand it very well. It's even very hard to simulate in a supercomputer, and we certainly haven't been able to replicate neutron star conditions, even for a moment in a lab on the Earth. So strange matter is pretty much a speculative topic at this point.
All right, the next question is from Cackling Clown, who asks, what are your views on using artificial intelligence for rover maneuvering and detecting different significant minerals on other celestial bodies?
Well, it's an important method, and it is being used more and more. And it's been a sort of gradual progression. So the Spirit and Opportunity, the 2 small Mars rovers that did their work for a long period of time, one of them lasted, I think, 13 years, they were not using full-on AI and machine learning. They were pretty much programmed every day. The team would get together each Martian day and decide what the rovers would look at. Now, they have to use some form of AI because you can't have real-time control of a Martian rover because the signals can take anything from 20 to 45 minutes to reach Mars, right? So you're not doing this in real time. So the rovers have always had some autonomy of their decision making. The current rovers, well, of course, we're talking about Opportunity, Spirit and Opportunity were two from really over a decade ago. The current rover, Perseverance, has a much higher capability, and it is actually able to use AI to plan its next route. Now, what that involves is a whole set of things. That involves safeguarding the rover. So a good part of the AI involves positional awareness of the rover, a sense of whether it gets to a dangerous tilt angle or the softness or hardness of the rock and the soil that it's traveling over. But it also involves decisions about the likely importance of the objects it's seeing. So it's scanning its surroundings, looking at the reflectance and the color and the shape and the texture of the rocks, and comparing against the database of the types of rocks that the Martian scientists anticipated. And so they have started using AI in a pretty advanced way with the Perseverance mission. Scientists like to be in charge. They like to exert their own expert opinion, though. So at no point has Perseverance been given over fully to become an AI-guided mission. But they are definitely using AI in the mix. And occasionally the AI will come up with suggestions, or why don't we look at that rock, or really you don't want to go in that direction because you're going to take the hazard level a little high, where the scientists and the mission controllers will completely defer to the AI.
The next question is from Rahul Kumar, who sent an email asking, if it is true that every natural process works according to some law, then how are those laws of the universe framed?
Well, that's a big question, almost a philosophical question. In fact, physicists of great caliber like Stephen Hawking and others have wondered where the laws of the universe come from. So if the universe is governed by physical law, which we think it is, that would include like quantum mechanics for the operation of small particles at the level of an atom, and general relativity for the way gravity works and the way mass and energy operate and space-time is curved. Where do those laws actually originate? Well, they were built into the universe as it started, because the entire universe since the Big Bang has been governed according to these same physical laws, and these physical laws haven't changed over 14 billion years. The universe has changed enormously. So I'm sort of dancing around the question of where they came from, because the simple answer is we don't know. They were built in on day one. And it is becoming a philosophical question because we don't know what caused the Big Bang. We don't know what the precursor state might have been, if there was one. That might possibly inform us where the physical laws came. They might just be happenstance. If you believe in the multiverse idea, where the universe was a quantum creation event and there could have been other quantum creation events, then those other universes in the multiverse could have completely different physical laws. And that would mean that the physical laws we experience are a product of chance or happenstance. That's certainly a possibility.
The next question is from Andrew Spaz, who's on with us live. Given that general relativity becomes unpredictable near, I assume t equals 0, I'm assuming they mean the beginning of the universe. And since cosmic inflation relies on a singularity, do you think there was really a singularity? Do you think that's an accurate or true theory for the beginning of the universe?
It's a good question, and actually the truth is that the theory does not require singularity. So there's a little bit of a misconception about the Big Bang, that the Big Bang was a singularity. It sounds like it, and if naively you project back the expanding universe to the first instance, you do seem to converge towards a singularity, the self-focusing, if you like, of the high density of matter and energy in the early universe does point back to a singularity. Ironically, it's inflation as an idea that finesses the idea of a singularity and says that a singularity is not necessarily the origin of the universe or description that we have to use. And that's because inflation as a mechanism takes a patch of space-time, but it's not an infinitely small patch. It's a patch of finite size, incredibly small, but finite size, and expands it exponentially such that the basis of our universe becomes a region of space-time that has been stretched flat by inflation. So because inflation starts with a finite patch of space-time and then expands it exponentially, that is the origin point of our description physically. And so you do not have to have a singularity in the Big Bang model if you are using inflation.
Excellent. The next question is from Koryatug, who asks, can you please talk about strangelets and voids? And do you believe that strangelet particles can exist? And if so, then how?
I'm going to have to punt because I've never heard of this word, strangelet. So we'll
Okay.
do this again in the future if I can figure it out.
Sounds good. Zaid 147 says, in about 5.4 billion years from now, our sun will turn into a red giant and possibly eat Mercury, Venus, and Earth. Pluto seems like it might be in the habitable zone, if I am not mistaken. And since it will be warmer, do you think life could start there, or could humans travel there as a new home?
Right. So the sun's fate has interesting implications, as the questioner suggests. It's correct. The red giant phase, where the sun ejects a giant cool envelope, but the envelope itself is plasma, will engulf the Earth and get close to the orbit of Mars, as I understand it, for the sun. So the habitable zone, as the sun in this bloated red giant phase, is very luminous and very large, physically large. That's right. The habitable zone will move out dramatically in the solar system. I think it encompasses the last two gas giant planets and Pluto. And so Pluto, yes, potentially it becomes marginally habitable. Unfortunately, the red giant phase of the star is a transient phase. It lasts maybe 100 million years or so. It's a long time, of course, but it's a small fraction of the time of the sun as a main sequence star. So by then, I mean, if we haven't figured out how to survive without a star, which seems like we should be able to figure that out, then just moving to Pluto because it ends up being habitable seems like a unlikely scenario. But of course, it does potentially mean that life could get started on Pluto in this distant future, which would be very interesting.
The next question is from one of our live participants. Why are planets and stars spherical in shape, but asteroids and comets are irregular in shape?
So the shape of astronomical objects essentially comes down to gravity. So gravity is a universal attractive force. And so when you have a physical object, an object that has collapsed for some reason because of gravity, then the gravity, of course, goes inwards in all directions. And the most end state of a natural object with gravity operating with equal strength in all directions is a sphere, because that's the most high degree of symmetry. So all objects bound by gravity, whether they're made of gas, liquid, which is very unlikely, solid, or plasma potentially, will take a spherical shape. And so stars all take spherical shapes, where the only deviation from that is because they have angular momentum and they're spinning. So they're oblate spheroids, slightly thicker at the equator than the poles. Planets beyond a certain mass also take a spherical shape, because when they form, they're made of essentially semi-molten material, so that it's viscous and it will move, and so they can alter their shapes to form a sphere. And the boundary of an object, which is where gravity is just insufficient to force it into this equal energy or most symmetric configuration of a sphere, corresponds to comets and asteroids. So all comets are small, 5 to 10 kilometers across. A lot of asteroids are that small. Biggest asteroid is Ceres, 1,000 kilometers. And that sort of roughly forms the boundary. You can see that the Mars moons, Phobos and Deimos, which are, I think, a few hundred kilometers across, they're potato-shaped, so they were not big enough to form spheres. So you can pretty much look at the asteroids or small moons of the solar system and see where the boundary is between things that always will go spherical because of the gravity force, and things that will not go spherical because the strength of the rock is sufficient to resist that tendency towards symmetry.
The next question is from an email. John asks, what are the sizes of the stable and unstable Lagrange points, and how many spacecraft can safely be stationed there?
It's a good question. I mean, because they are called points, then mathematically they are indeed points, which is to say, if you have a gravitational situation, you can identify a point in space at which the gravitational balance is maintained that corresponds to a Lagrange point. Some of those balance points or Lagrange points are stable, where an object displaced from the actual point will move towards it, and some are unstable, where an object at the point displaced from it will drift away from it. But they are actually points. The question of how large operationally they are is a question of which Lagrange point you're talking about and whether you're talking about the Earth, Sun, Moon system, which is usually what people are talking about. And there the answer is a few thousand kilometers. For a spacecraft that's at an unstable Lagrange point, it can drift by a few hundred kilometers, and very modest restorative forces would put it back right near the Lagrange point itself. So they don't have to be absolutely located at one fixed point in space. There's a margin, and that margin of error is tens, maybe a few hundred kilometers. Beyond that, you start to need large restorative forces, and that means you're essentially drifting away from the stable point.
The next question kind of goes back to our Martian radiation shield conversation earlier. Would such a structure require a lot of energy? How much would it require, and how large of a field could be created to protect humans on Mars?
So there are various ways you could create an artificial magnetic or electrical field. We can do this on the Earth, and this is the idea of doing it out in space to create an artificial field to protect Mars, say, or for any purpose that we might find. Essentially, you need particle accelerators. You're trying to create a plasma, because when you separate neutral atoms into their charged constituents, then automatically by moving those charged particles around, you can create a magnetic field, because moving electrically charged particle creates a magnetic field. That was demonstrated by Faraday hundreds of years ago. So that's a basic way we do it. We take neutral matter, turn it into a plasma, create charged particles, accelerate the charged particles, and their accelerated motion induces a magnetic field. So that's how we would do it. So terrestrial technology that's never been scaled up to the level that we would need to shelter a planet like Mars. So it's a prodigious experiment if you had to do it in space. So it's not impossible, but it's probably extremely expensive and difficult.
All right, the next question is from one of our live participants. Are we safe from asteroids, or can we change the path of asteroids that could hit the Earth in the future?
We're not safe from asteroids in the long term, because we know that significant sized asteroids hit the Earth, significant enough to cause global or catastrophic damage to a large part of the Earth every 50 to 100 million years. So we know it's happened a few dozen times in the history of the Earth, and there's no reason that will change in the future. We have pretty good monitoring to know where big enough objects to cause real harm are in space, going out to the asteroid belt or coming in from the asteroid belt on Earth crossing orbits. And then the question of what could we do about it is we pretty much know what we could do about it, because we've already rendezvoused with comets and asteroids with our spacecraft. And all you have to do beyond that is rendezvous with an asteroid that might hit the Earth, tether to it, explosive bolts or some other mechanism to tether the lander into the asteroid. And then if that lander has rockets or jets or retro rockets, you can use those rockets to generate motion for the asteroid and alter its trajectory. So those technological tools all exist, and they've been demonstrated, prototyped, including the rendezvous part. And if you had an asteroid on a collision course with the Earth, our monitoring is good enough to pick it up years before it gets here, several years. And that's actually long enough to make a rendezvous mission to change its trajectory. So that pretty much covers the danger from asteroids. We figured it out. We know where they are. They're far enough away we'd have time to get there, and we have a means to change their path.
So as a follow-up to the question about Lagrange points, I don't remember if you addressed this specifically, but will spacecraft that are stationed at Lagrange points need fuel to maneuver to maintain station and or avoid other spacecraft?
Yes, in almost every case they will need that, because the Lagrange point that's the most heavily used by NASA, for example. The James Webb is going to go to this Lagrange point. The WMAP satellite that did microwave observations, and a number of others, I think half a dozen others, are going to one of the unstable Lagrange points. So they will all need adjustment over time to keep them in a stable location. The gravitational potential, though, at these balance points is fairly shallow, which means you don't need an awful lot of energy for a modest-sized spacecraft to keep it in place. So these will need minor, modest corrections, which can be done over the years and not even use a lot of rocket fuel.
The next question is from Zorukal, who is on live with us. Can a rogue planet support life through volcanism or some other source of energy?
Sure, absolutely, it's possible. So first of all, rogue planets is an interesting term for what astronomers hypothesize is a potentially very large population of exoplanets that are out there with no parent star. How can this happen? Well, in the formation scenarios of solar systems and in all the simulations we run of how solar systems form, in the early chaotic phases of a solar system, it's very easy, and it happens very often, that planets get ejected. They form and then they're ejected due to instabilities or resonances. And in some of these simulations, you have as many planets ejected as remain in the system. So some substantial fraction of all the exoplanets we might catalog, there's another substantial fraction of those that are out there in space with no star, and those are the rogue planets. We've inferred the existence of them by microlensing techniques, but really we haven't directly observed them, but they're hypothesized to be out there. And yes, if a rogue planet was large enough to retain a thick atmosphere, and therefore also large enough to have active volcanism, there's no conceivable reason that it or some subset of the rogue planets couldn't be habitable and have developed life independent, not needing a star. There's life on Earth that doesn't need direct solar energy to persist. So we know that it's possible.
The next question is from Christina, who sent an email to us. What is the difference between a nebula as a remnant of a star and a nebula as a star-forming region?
Nebula is a nebulous word, as you might imagine. So astronomers use nebula for multiple purposes, and so there isn't a difference. It's just a multi-use word, if you like. Nebula just means sort of gauzy luminosity, sort of soft light that doesn't have a sharp edge or a natural demarcation or is not symmetric, irregular shaped, if you like. And so a lot of nebulae, I mean, remember the nebulae were first found by Herschel and Messier back in the 18th century, late 18th century, and that's where the first word nebula comes from. And the nebulae, for instance, in the Messier catalog are a wide variety of things. They range from star-forming regions to evolved stars with shells around them, to supernova remnants, so dead stars, and so on, and to galaxies. So because originally the extragalactic nebulae were what we call galaxies. So this word is just used in multiple situations, and astronomers then have to get more specific with their description to say what they're actually talking about.
All right, the next question is from Wendy, who asks, what is your opinion as to whether dark matter may have formed during inflation prior to the Big Bang, as one scientist has proposed, and perhaps that's why it is so hard to pin down?
Well, I'm not sure we know about inflation prior to the Big Bang. We don't really have a physical theory for prior to the Big Bang. The role of dark matter in inflation is not obvious because the mechanism for inflation, this hypothetical exponential expansion of the infant universe when it was really super small size, subatomic size, does not involve dark matter at all. The field or the motive force for inflation is likely a grand unification scenario involved in the three of the forces of nature combining together into a super force. And so dark matter is not implicated in that. So really, inflation and the very early universe do not speak to dark matter at all. And the dark matter in the universe doesn't become significant. Obviously, the particle, the dark matter particle, assuming it's a subatomic particle, which is as abundant as electrons and protons and neutrons in the universe, more abundant actually, was around from the beginning. But it didn't actually influence how the universe behaved until quite a while after the Big Bang.
The next question is from Bo Bogan, who asks, what is the best university, or which is the best university for an astrobiology degree?
That's a good question. There are not that many astrobiology degree programs in the world, let alone in the United States. And there are certificate programs, which is a more modest qualification where you'd have to take some graduate courses perhaps, or some undergraduate courses and get a certificate. I think the one with the longest track record and the best track record, because you can say what happens with its graduates over a period of 20 or plus more years, is at the University of Washington. So that they have a PhD program, and a certificate program, and they've been graduating people for a long time, and their graduates are now in leadership positions in astrobiology. So that would be my choice for the best program, just because they have such a long track record and some very illustrious graduates.
Mark Laufenberg asks, what are the significant steps that determine whether a forming galaxy evolves into an elliptical or a spiral galaxy?
I think the fundamental criterion is the angular momentum of the nebular cloud, the diffuse cloud of intergalactic dust and gas that collapsed to form the galaxy is. If it has a very small amount of angular momentum, then it will tend towards spherical collapse, and that naturally will lead to a very rapid star formation of stars that then take elliptical orbits and form the halo of the galaxy, and so you essentially have an elliptical galaxy. If it has a large amount of angular momentum, then the collapse will preferentially occur along the rotation axis, and the compression of the gas and its differential rotation will lead to star formation in the disk, and so you have a spiral galaxy. So if it's just one thing, it's essentially the angular momentum of the gas cloud before it starts collapsing.
Our next question is from a live participant. The general question is, what is a quasar? And the specific question is, why do some consider quasars as primordial galaxy nuclei?
So to answer them separately, what a quasar is a quasar is an acronym, or it's a contraction of quasi-stellar radio source, because back in the 1960s, radio astronomers found sources of intense radio emission, and normal stars do not emit radio emission, so that was an immediate marker of something strange going on. And when optical astronomers found counterparts, they found intense and very small regions of optical emission. And eventually figured out these were distant galaxies producing enormous luminosities. Now, quasars don't have to be radio sources, which turns out 90% of them are not radio emitters, but they all have intense optical emission. And we think it's accretion energy around a supermassive black hole. So that's the general picture of what a quasar is. Now I've forgotten the second part of the question.
Do some people, or why do some people consider them to be primordial galaxy nucleus?
Yeah, quasars are not necessarily primordial galaxies or their nuclei. Quasars actually did not form at the beginning of the universe. So in a sense, they're not primordial galaxies because they're not the first galaxies we see in the universe. So it turns out there is a peak to quasar, the demographics of quasars, where people have counted how many quasars there were per unit volume of the universe over cosmic time, or what their peak luminosity was. That has a rise and then a fall. So quasars take a while to form because you have to grow a supermassive black hole to significant size, and that turns out to take about 1 billion years or 2 billion years. Then they have their peak of accretion power and luminosity, and then they gradually fade because they run out of fuel individually, or on a larger scale, the universe expands to the point where it's hard to form new compact objects. So people have mapped this history out now, and the peak of quasars, in terms of their brightness individually and their number density collectively, occurred about 3 or 4 billion years after the Big Bang. So not at the beginning of the universe. There were plenty of galaxies before there were quasars. And in fact, you had to have mature galaxies before you can grow a supermassive black hole that is a quasar power source.
All right, we just have time for a couple more questions, and then we will be wrapping up for today. The the second to last question is, could you kindly speak about singularities in black holes and the purpose of the singularity?
Well, the singularity, rather than having a purpose, is sort of an inconvenience because it's a prediction of the theory of black holes, of general relativity. The prediction is that when matter reaches a density where it develops an event horizon, and that means that there's a region within which everything is invisible to us because no light, no matter can escape. The interior to that represents a region of such intense gravity that in the theory, you predict a cusp of mass density, and that's a singularity. So it's a prediction. It's not been verified because we've never seen inside a black hole, and maybe we never could see inside a black hole. It's an inconvenience, or it's actually a problem with the theory, because anytime you have an infinity of a physical quantity, whether it's infinitely small or infinitely large density, that tells you something's wrong with the theory. That's unphysical to have an infinity in a physical theory. And so it's been known for a long time, since the 1970s, that the black hole theory shows that general relativity is incomplete. The existence of black holes and their implied singularities mean general relativity is lacking in some way. And so that's part of the motivation that astronomers have to develop a new and different and better theory.
All right, and the final question for today is from one of our live participants. Is the flatness problem of the standard Big Bang model really a problem, and how much of a problem is it?
The flatness problem is a problem of the Big Bang, and I should summarize what it is. The flatness problem stems from the fact that by observation, using microwave background radiation most effectively, we can show that as light travels through the universe, it is almost not deviated at all in terms of space-time curvature. And essentially, we can show that the global curvature of the universe, the visible universe that we can examine, departs from flatness by less than about 1%. So it's extremely flat. The reason why this is an issue for the standard Big Bang is if you trace the expansion backwards, then you inevitably point to a time early on when space curvature must have been extreme because of the mass density was so high. And so it actually requires what's called fine tuning, which means you have to actually tune the theory very specifically to arrange that after so much time, you'd end up with perfectly flat space, given that it started very far from flat. And so the inflation idea is a way to avoid that being fine tuning or an accident and turn it into a natural or inevitable consequence, because inflation takes tiny curved space-time and blows it up to be globally flat and then continues the more regular Hubble expansion. So naturally, that's what we see, flat space around us. Okay, that was great. Good range and coverage as always. And thanks for your questions. Thanks to Vicki and Matthew for running the show. And I'll be with you I'm taking a little vacation for 10 days. So I think we're having 2 weeks off, but we'll be back with you in a while.
Excellent. Thank you, everyone. And make sure you stick around. We are going to go right into our next stream where Vicki is going to be playing the game Outer Wilds, which is a beautiful space exploration game with a mystery to solve. So so Chris and I will take off, but stick around for our continuing stream. We appreciate you and are looking forward to the next stream. Take care.